Hi, today we're going to work on lesson 20.2, algebraic representations of dilations. Yesterday we worked on what a dilation is and how to find the scale factor. Today we're going to continue on now algebraically representing that. And in case you struggled through yesterday, we're able to kind of make those connections today as well. So graphing enlargements. Let's take an activity to understand algebraically how dilations work, whether we're sizing it down or sizing it up, right? Reducing or enlarging. So when a dilation in the coordinate plane has the origin as the center of dilation, you can find points on the dilated image by multiplying the x and y coordinates of the original figure by the scale factor. For scale factor k, the algebraic representation of dilation is xy, the original coordinates, becoming now k times x and k times y. For enlargements, k is greater than 1, right? That makes sense because if I want to enlarge something, I need to make it greater. And if I want to reduce something, I'm going to multiply by something like a scale factor of a fraction. So let's work with part A. It says the figure shown on the grid is the pre-image. This blue piece is the pre-image. The center of dilation is the origin. It wants us to start off by listing the coordinates of all of the vertices of the pre-image in the first column of the table. And you're not always going to get a column to write into, so it's always best to kind of create your own. Label it pre-image and image, and I always write out the vertices first, the coordinates of the vertices, so I know that I'm working with those specific factors of x and y, and I'm able to more easily work without the algebraic enlargement or reduction that I need to work with by multiplying. So for the pre-image, it starts us off at the point 2, 2. Let's go ahead and graph the rest. It doesn't matter which order I go in. Let's go to 2, negative 1. Then we'll go to 1, negative 1. Then we'll go ahead and write out 1, negative 2. Then we'll do negative 2, negative 2. Now we're at negative 2, positive 1. Then we're at negative 1, positive 1. And then we have negative 1, positive 2. And here, if I look at the new image, the algebraic enlargement that it's asking us to work with, or the dilation, has a scale factor of 3, because it's asking me to multiply my x's by 3 and my y's by 3. That means I'm enlarging everything by 3, a multiple of 3. So in the case of 2, 2, this vertex, it is now becoming 6, 6, because we've taken 3 times 2, made it 6, and 3 times 2 made it 6, right? 3 times our x, 3 times our y. So I will now plot 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Okay, and this should be an enlargement of this pre-image. Let's move on to the next coordinate. I have 3 times x now, so 3 times 2 is 6, and 3 times negative 1 is negative 3. So I will graph 6, negative 3. Okay, then we'll go ahead into 1 and negative 1, so 3 times 1 is 3, 3 times negative 1 is negative 3, so 3, negative 3. Then we have 1, negative 2, so 1 times 3 is 3, negative 2 times 3 is negative 6, so I will do 3, negative 6. Then we have negative 2 times 3, which is negative 6, negative 2 times 3, which is negative 6, so negative 6, negative 6. Then we have negative 2 times 3 is negative 6, 3 times 1 is 3, negative 6, 3. Negative 1 times 3 is negative 3. 1 times 3 is 3. So negative 3, 3. And then negative 1 times 3 is negative 3. 2 times 3 is 6. So negative 3, 6. And now we will connect all of our points as best as we can in a straight line. And see how this enlargement has worked itself out. So as you can tell, this new image is much larger. In this case, it's 3 times larger. Okay, so this is an enlargement. With a scale factor of 3, right? Because I multiplied every single vertex by 3. And actually the algebra here is what told me I am going to use a scale factor of 3. It says directly, multiply your x's by 3 and your y's by 3. Okay. So how did this dilation affect the length of the line segments? Well, if this line segment here is, for example, 1 unit long, this line segment is 3 units long. So how did it get affected? Well, the line segments are now 3 times longer. And how does the dilation affect the angle measures? Well, here I have a 90-degree angle, right? Because I know that where these x's and y's touch and create the lines for the coordinate grid, they're perfect squares, which means this is a 90-degree angle. In this case, that's still a 90-degree angle. It's still in that unit, that one coordinate, that square where the x and y touch. So the dilation does not affect angle measures. Okay. Now that we can work with enlargements, right, where we're multiplying by either whole numbers or decimals, fractions, but anything greater than 1, right? An enlargement would be anything times something greater than 1. Now we're going to work with reductions, where we're going to work with either decimals or fractions to reduce the size, meaning the scale factor has to be between 0 and 1. It can't be 0, because 0 would mean that all the x coordinates and y coordinates would multiply times 0 and become 0. So you would literally have every single vertex or point on the origin 0, 0, which makes no sense. And it can't be 1 because every x and y coordinate times 1 is going to be the exact same thing. So the pre-image would be the new image, and that would not create any kind of dilation. Nothing enlarged or got smaller. It stayed the same. So it has to stay between 0 and 1 for it to be a dilation. In this case, a reduction. So it is telling me that my algebraic representation, or the algebra that I should use to work with this dilation, is multiply my x's and y's by a half. Since it's half, anything I multiply times half I know is going to get smaller, so that's a reduction automatically. So first I want to list the coordinates of what I have. So we'll start with the tip point of this arrow, which is at 0, 5. Then we'll move on this way to 4, 2. And right now all I'm doing is finding each coordinate of the vertexes. Now I have 2, 2. I have 2, negative 4, 2, negative 4. I have negative 2, negative 4, negative 2, 2, and negative 4, 2. Okay, using a different color just to be able to visualize better, I'll go ahead and complete the algebra for this dilation and the reduction, and we're going to go ahead and graph all of the points and create the reduced arrow. So I will use this algebra 1/2 times all of my x's and 1/2 times all of my y coordinates to find the new image's points. So for example, 0 times half is still going to be 0, but 5 times a half is going to be 2.5. So I will graph 0 and 2 and a half right there in the middle. Moving on, everything times half. 4 times half is 2, 2 times half is 1. And I'll plot 2 and 1. 2 times half is 1, 2 times half is 1. So I will plot 1, 1. 2 times half is 1, negative 4 times half is negative 2. So I will plot 1, negative 2. Negative 2 times half is negative 1. Negative 4 times half is negative 2. Negative 2 times half is negative 1. 2 times half is 1. And then negative 4 times half is negative 2. 2 times half is 1. Negative 2, 1. Now we will go ahead and connect the arrows to see this reduction in size. Right? And since I multiplied everything by half, this new image should be half the size of the pre-image, which makes sense, right? The scale factor in this case is listed right here in the algebra, which is half. Now, did the dilation affect the length of the line segments? Just like in the last one, yes, it does. Because here I have, for example, a length of 1, 2, 3 for the side of this dilation and a length of 1, 2, 3, 4, 5, 6 for the pre-image, meaning that the lengths are half as long. Half as long, I apologize. You could say half as long as the lengths of the pre-image. And then how would a dilation with a scale factor of 1 affect the pre-image? Well, like we said, the pre-image would stay the same because anything times 1 and it is itself, meaning that our shape would not increase in size or decrease in size. Let's go ahead and move on. Now, what if the center of dilation is outside the image? The center of dilation can be inside or outside the original image. In the dilated image, the center of dilation can be anywhere on the coordinate plane as long as the lines that connect each pair of corresponding vertices between the original and dilated image intersect at the center of dilation, right? In that case, it's going to be our images being on 2 separate locations in the coordinate grid, however, still being able to interact or intersect. So graph the image of triangle ABC after a dilation with the origin as its center and a scale factor of 3. What are the vertices of the image? So the fact that it's telling me it has a scale factor of 3 means I am multiplying by 3. And not just one thing by 3, but both my x and y coordinates times 3. So in this example, it gave us the coordinates for A as 1 and 1. We would multiply by our scale factor to say 1 times 3 is 3, and 1 times 3 is 3. So the point for our new image, A, would be 3, 3. So this would be A prime. For B, they gave us 3, 1. So I would multiply both x and y by 3. So I would get 9 and 3, and I will plot those. And then for C, we have 1 and 3 as the coordinates, so we would multiply both of them by 3. 1 times 3 is 3, 3 times 3 is 9. So 3, 9. C prime. Now I'll go ahead and connect. Right? And we have our new vertices, and as we see here, on step 2, we notice that it is an enlargement. Since we're multiplying times a k, or a scale factor greater than 1, we're obviously enlarging. Anything less than 1 would mean that we are reducing in size. Now, it says that the lines can connect each pair of corresponding vertices between the original and dilated image, and they intersect at the center of dilation. Well, these do intersect at the center of dilation, right? Okay, so they are a good dilation of the other. It's asking us to graph the image of XYZ after a dilation with a scale factor of 1/3. Let's have you guys try number 5, right? 1/3 is telling us, or is between 0 and 1, which should give us a hint as to whether we are working with a reduction or an enlargement. The origin is the center still, so we're still focused here. And it wants us to describe an algebraic rule as well. The algebraic rule looks something like what we did here, where we had 3x, 3y. 1/2 x, 1/2 y. So you would actually be labeling the coordinates and then telling us. Go ahead and try number 5 on your own. Pause the video and let's see how it works. For those of you who stayed on, let's continue. The first thing I want to do is write the coordinates of the points that I have. X, Y, and Z. For X, we have 3, 3. For Y, we have 9, 9. And for Z, we have 3, 9. The reason I do that is because I want to be able to work with the algebra, but I need to actually visually see what I'm working with, not just plotted, but I want the numbers so that I can do the math in my head or on paper. So this is the new image. I'm going to use this rule of 1/3 as a scale factor to reduce the size of my new image because it's between 0 and 1, so I'm working on a reduction. So 1/3 times 3 is 1, and 1/3 times 3 is 1. So my new point for X is 1, 1. 9 times 1/3 is 3, and 9 times 1/3 is 3. So I'm going to plot 3, 3. And then 3 times 1/3 is 1, and 9 times 1/3 is 3. So I will plot 1, 3. Now these have a point that actually does intersect. It is point Y prime with X. Here we have Z prime, and here we have X prime. And they do intersect, okay, at the center there. So they are a dilation of one another. Now the algebraic rule that I would want to use is that original X and Y would now become, and we always want to start them out this way, the original X and Y would now become 1/3 of what the original was and 1/3 of what the original Y was. This is our rule. So all you're working with today is figuring out whether you're dilating to enlarge or dilating to reduce based on whether the number is greater than 1 or less than 1, right? Between 0 and 1. Anything between 0 and 1 is a reduction. Anything greater than 1 is a dilation, is a enlargement. They're both dilations. And then you multiply your X's and Y's to get the new points for your coordinates. Your homework is going to be working on page 643. And we're going to go ahead and have some practice online with some of the tools that we have like MobyMax and Khan Academy. Good luck!